Now here's what we do in order to allow cars to go around curves a little bit faster is we bank the track, so to speak. You'll recall, if you've ever seen NASCAR or Indianapolis Speedway or something like that, that all of those tracks are banked. And this is essentially to increase the speed that's allowed, that allows those cars to go around the track so they can go around the curves faster and you have a more exciting race. And so we're going to do a few calculations to show how calculating centripetal force helps you understand what banking you need depending on what your situation is. Now, ideal banking is the angle of banking where the external forces are equal and the horizontal force, the external forces, that is the force that would send the car off the road, is equal to the centripetal force in the absence of friction. And so ideal banking, if you can think about it this way, if this car were just sitting there and there were no friction, it would then slide down this way. And so ideal banking is the amount of centripetal force necessary to prevent that slide from occurring. And what you see here is that this force is going to be equal to n sine theta due to the weight of the car. And that has to be equal to the centripetal force. And for those two to be equal, this angle has to be a certain amount. And so that's the ideal banking. So here's a calculation. We know that the n sine theta is the parallel force due to the weight of the car, and it has to be equal to the centripetal force, which is calculated here, mv squared over r. We also know that the weight of the car is mg. So if you set those equal to each other, you end up with n over this and this over this. So n sine theta over n cosine theta equals mv squared r over mg. If you cancel out the m's, you end up with v squared over rg. And sine over cosine is tangent. And then if you solve for theta, you get the arctangent is equal to this. And this gives you the ideal banking for any particular curve with no friction. And this is a formula that you should remember. If we have this pictured car above, what would be the, and the radius of curvature is 100 meters, the banking is 65 degrees, what is the maximum speed that this car can go around this curve with no friction? Now you can also use this, you can put 65 in here and find out what the maximum velocity v is for this to be an equilibrium. So we have to first we have to rearrange our equation. So we start out and we turn this into tangent theta is equal to v squared over rg. Okay, we're wanting to solve here for v. Okay, so the next step would be to move this over this way, and so now we have rg tangent theta, the square root of that is going to equal v. Now we can put our numbers in, and our numbers are 100 for the radius, g is 9.8, and it's the tangent of 65 degrees. And so if you do the math on this, you get 45.8 meters per second square per second, excuse me. Now remember, that's with no friction. Okay, it all changes if we include a friction. So that is actually fairly fast if you think about it. in a situation where there's absolutely no friction. Let's talk for a minute about something known as fictitious forces. A fictitious force is something that's perceived but not real. Let's pretend for a second that we have a car. We're driving down the road in this car. This is a woman, so let's say this is Becca driving down the road in a car, and she turns right. When she turns right, she will experience what occurs in diagram A. She will feel her body moving up against the side of the car. Now this force that she feels is relative to the car. It's a fictitious force because the force she feels is only because the frame of reference is the car. The true force is actually in diagram B. In the Earth's frame of reference, the actual force that occurs is the centripetal force, the force that causes the car to make the turn. As it says here, the driver continues to move in a straight line in relation to the Earth. The car moves to the right. There's no real force to the left. The real force is the force that pushes her to the right along with the car. So the real force, what she feels, is what appears to be her being shoved to the left, but what's really happening is the car is moving to the right, she's moving straight ahead, and that's what the force she feels. That's why this is called a fictitious force. It's what's called centrifugal force. Centrifugal force. I'll emphasize the second syllable so you know exactly what I'm saying. Here's another example. In A, you have a person sitting on a horse. And as this person goes around, they feel like they're going to be thrown off to the outside. This is, again, a fictitious force. What's truly happening is they're heading straight ahead and the horse is headed to the left here. And so their perception is that they're being thrown to the right off, but the real force is the force that keeps them on the horse moving around. And that's what's shown in diagram B. For the proper frame of reference, the real force is toward the center of the circle. The real force is the centripetal force that's needed to cause the circular path of both the horse and the rider. Now, let's change gears completely and start talking about some gravitational laws. The first one we'll talk about is the universal law of gravitation that Newton first wrote in the Principia. The universal law of gravitation states that every particle in the universe is attracted to every other particle in the universe with a force that's along a line that connects those two masses. So every object, no matter what object it is, there's a force that attracts these two objects to each other along this line, and there's a force for each object. And that gravitational attraction is along the line of the centers of mass. And the magnitude of that force is the same, one direction or the other, consistent with Newton's third law. And the formula for Newton's universal law of gravitation is shown here. It's equal to G times the mass of one object times the mass of the other object. Frequently it's shown as a small and an uppercase M because frequently one of the two objects is very big and the other is very small. And then the square of the distance between their centers of mass. The gravitational constant has been calculated out as 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. That's a formula that you need to remember. And that formula, interestingly enough, will show up in other forms as we move through physics. So here's a example of the actual path that the sun takes. And one of the things that's very interesting is you notice you have the Earth here and the moon here. And the Earth and the moon are traveling together, and because of the effect of the moon's gravity in this process, the actual motion is a little bit of a wiggle depending on where the moon is in relation to the sun. So sometimes, well, when I talk about tides, there's a picture that shows the different tides, and when the moon is on the inside, there's an increased motion in this direction, and when the moon is on the outside, there's an increased motion in this direction, and that's why there's a wiggle in the path. It's been exaggerated here so you can see it. Now, to calculate the acceleration due to Earth's gravity on the moon's surface, we have to take the Earth's mass, the moon's mass, and work with that. And here is that. To calculate, you remember that gravity is equal to mass divided by weight. And so we can rearrange the gravitational law to take that into account, so that the gravitational constant times the mass of the Earth times the distance between the two squared. You put the numbers in. This is the mass of the Earth in kilograms, and this is the distance between the two in meters. If you calculate that, you get that the gravitational effect of the Earth on the moon's surface, is equal to this, which is quite small. Now you can calculate, so that's the gravitational force that's drawing the moon towards the Earth. So what's the centripetal force needed, or acceleration needed, to keep it in orbit to counterbalance that gravitational pull? Gravitational acceleration is equal to the radius times omega squared. Omega is 2 pi radians for a complete circumference, and it takes 27.3 days for the moon to go around the Earth, and there are 86,400 seconds in a day. So if you do this calculation, it's 2.66 times 10 to the minus 6 radians per second. That's the angular velocity of the moon around the Earth. The acceleration, centripetal acceleration, is now going to be equal to that radius times the angular velocity squared. And if you do the math here, you get 2.72 times 10 to the minus 3. So that's the centripetal acceleration necessary to keep the moon in its orbit. Now this is the diagram I was going to tell you about. When the moon is out here, the Earth would tend to be drawn in this direction. When the moon is in here, it would tend to be drawn in this direction, which is why you have that wiggle in the path. The spring tides, the moon is both on this side and this side, so the tides are higher. The neap tide is when the moon is on this side or this side, and there's still a tide, but it's primarily due to the sun and counterbalanced by the moon. So it's a lower tide. The spring tides are the high tides that are caused by the cooperation between the force caused by the moon's gravity and the force caused by the sun's gravity. I'm going to end this part here, and the third part will be a brief discussion of Kepler's laws of planetary motion.